All right, we're starting in on chapter 21, which is called More About Tests. So we're still going to be dealing with confidence intervals and significance tests for proportions. So just a little bit more specific details. Now remember that low p-value means that you reject H naught. So when our p-value was low, and in general 0.05 was kind of your estimate, that's how you would know if it's low that you would reject the null hypotheses. But sometimes you kind of want to know, well, how do you know what's considered low? And again, I gave you kind of our rule of thumb, but often we are given a value to compare with the p-value in order to make a decision, and this is called an alpha level. So you'll actually be given a value to use to make your decision. Now, the most common alpha levels, alpha equals 0.05, is very common. So that's one of your more common alpha levels. This is the symbol. We use the Greek letter alpha for alpha. And what that would mean is if you are given to use an alpha level of 0.05, then if the p-value is less than 0.05, we reject H naught. So what we're going to take a look at now is question 4. So this is in your textbook on page 491. You might want to look there. Environmentalists concerned about the impact of high-frequency radio transmissions on birds found that there was no evidence of a higher mortality rate among hatchlings in nests near cell towers. They based this conclusion on a test using alpha equals 0.05. Would they have made the same decision at alpha equals 0.10? How about alpha equals 0.01? All right, so what is this basically saying then? We're told in the problem that they found that there was no evidence of a higher mortality rate. That means that they would have failed to reject. So they failed to reject H naught because they found no evidence. So if they failed to reject H naught and they were using an alpha level of 0.05, then that means that their p-value was greater than 0.05. So we know that much. So then we're asked, would they have made the same decision at alpha equals 0.10? Well, we don't really know, because all we know is that the p-value is greater than 0.05. So they would have made the same decision if alpha, or if the p-value was greater than 0.10, then yes, they would have still rejected H naught. So the answer to that first part of the question, I'm going to call that part A. So the answer to part A, we don't know. If the p-value was greater than 0.10, same decision. Right? If the p-value was in between 0.05 but less than 0.1, and that was their alpha level, then we would end up rejecting H naught. So then part B, how about alpha is 0.01? Well, for that one, since the p-value is greater than 0.05, then that means it's also greater than 0.01. So the p-value would be greater than 0.01, so they would fail to reject. Remember, low p-values reject H naught. So, and even though you might look at something like that and say, well, 0.02 would be low, but if your alpha level is 0.01, you would have to be below your alpha level in order to reject the null hypotheses. All right, the next problem I want to take a look at is also on page 491, number 6. A new reading program may reduce the number of elementary students who read below grade level. The company that developed this program supplied materials and teacher training for a large-scale test involving nearly 8,500 children in several different school districts. Statistical analysis of the results showed that the percentage of students who did not attain the grade level standard was reduced from 15.9% to 15.1%. The hypotheses that the new reading program produced no improvement was rejected with a p-value of 0.023. Then we're asked to explain what the p-value means in this context. What I'd like to start by doing is think about what our null hypotheses would have been, just to kind of practice that. So the null hypotheses would have been to say that that there was no improvement. So no improvement would mean that it remained at what it was before. So we would have p for our proportion equals 0.159. And so that would mean that the program was not effective. So our alternative hypotheses, we were looking to see that there was an improvement. Well, if there was an improvement, that would mean that the proportion of students who did not attain grade level, that would go down. So our alternative would be that the new program improves reading. Now, if we were actually doing a significance test, we'd have to go through all of our conditions. But they tell us what a p-value is, and they give us a p-value of 0.023. And then they ask, what does it mean in this context? So here's what we say. If the program was not effective, remember, that's like saying if the null hypothesis is true. If the program, but I'm putting it in context, if the program was not effective in improving reading, then the probability of getting results as extreme or more than ours let's say than our sample is 0.023. Okay, so that's how you would interpret a p-value. Now, I talked a little bit about this the other day in class. Part B says, even though this reading method has been shown to be significantly better because we had a low p-value, so we rejected the null hypotheses, why might you not recommend that your local school adopt it? And so in Part B, and I'm not going to write this down, but in Part B we talked a little bit about how it's not practically significant. If you look at the percentage rate, 0.159, 15.9%, to the sample results were 15.1%. Well, that's not much of a difference. And so remember what can sometimes happen. We had a really large sample size, 8,500 children. And sometimes having a really large sample size can lead us to a result that even though it is significantly different, which we've shown with a very low p-value, it's not really practically important. And so you do have to stop and think about things like that. For example, a new reading program would probably be very costly to the school district, and the gains that you might see wouldn't be significant enough to make it worth all the extra money that it would cost to do that. The next problem I want to take a look at is number 8, is the euro fare. Soon after the euro was introduced as currency in Europe, it was widely reported that someone had spun a euro coin 250 times and gotten heads 140 times. We wish to test a hypothesis about the fairness of spinning the coin. And part A, kind of a little bit of a review, estimate the true proportion of heads, use a 95% confidence interval, don't forget to check conditions first. So we're going to start by taking a look at the conditions. I think I'm going to make this a little bit smaller here. So for our conditions, we've got randomness, and we're flipping a coin. So since we're flipping a coin, we can treat each flip as random from a random outcome when you're flipping a coin, either heads or tails. Our second thing, we know that 250 times that you're going to flip that is less than 10% of kind of unlimited, because you could keep spinning or spinning the coin, spinning or tossing, spun, toss. Okay. The third thing, since it's random, each spin should be independent. And our last one, we're doing a confidence interval this time, so we're doing in p hat. So we're going to have, we had 140 heads. Oops. Which is definitely greater than or equal to 10. And n times q hat would then be 110, which is also greater than or equal to 10. So our conditions are met, which means that we have an approximately normal distribution, and our mean for this. Now our p hat value, all right, so it would technically be p, which we would expect to be 0.5, but we're going to use an approximation here, and so we'd have our standard error of p hat q hat over n. So, but actually we're going to be using our formula for our confidence interval. So our confidence interval formula, we are doing a 1 proportion z interval, and it's always a good idea to name whatever it is you're doing, whether it be a confidence interval or a significance test. Always name the interval or test. So our formula for that is p hat plus or minus z star times the square root of p hat q hat over n. And if you do this on your calculator, and I'm not going to go through the steps for that because we have reviewed that, we get 0.498, 0.622 for my confidence interval. And then don't forget, really our very important part of this is our interpretation. We are 95% confident that the true proportion of heads on the euro is between 0.498 and 0.622. So that's my interpretation, and that would be part A. And look back up here to see part B. Does your confidence interval provide evidence that the coin is unfair when spun? So let's think about what we think by fair or unfair. If we had a fair coin, so if it was a fair coin, we would expect to find a p-value, or we expect to find p equal to 0.5. So if we were doing a null hypothesis, we would probably say something like p equals 0.5, and our alternative, if it was unfair, we might say p is not equal to 0.5 if we were doing a significance test. And we can actually use our confidence interval to help us with our test. So when you look at your confidence interval, notice that 0.5 would be in the interval. And because it is in the interval, if we look back at what our question said, does your confidence interval provide evidence that the coin is unfair? No, it doesn't, because in this case, we found that 0.5 was within the interval. Barely, that's true, but our confidence interval then would not provide evidence that the coin was unfair. Now, one thing you do have to keep in mind is that when you do a confidence interval, remember that we were basing this on a normal distribution or a normal model. And so if we had a 95% confidence interval, we had 0.95 in the middle, we have two tails, and we would have 0.025 in each tail. Well, because of that, a confidence interval compares to a two-sided test. So that is actually one thing you would need to remember. A confidence interval compares to a two-sided test. And so for this part, in part C, we have a question. Part C asks us, what is the significance level of this test? So our significance level of our test would be the combined amount in both tails. Because I would be doing a two-sided test, then my alpha, or my confidence, my significance level, alpha, would be 0.05, because that was the combined amount in both tails. If I had been doing a test instead and calculated a p-value, had my p-value been less than 0.05, I would have concluded that the euro was not fair.